Hey there, we're going to go over some conservation of energy notes. Now, so far in this unit, what we looked at is work and power. And one of our equations for work, we said work was equal to the change in energy. So knowing this, if there is no work done on your system or object, that means that the energy within the system is conserved. And remember that word conserved there just means that it stays the same. Okay, kind of like in our conservation of momentum, the total momentum stayed the same. With energy, if energy is conserved, then the total energy of the system will remain the same. And in terms of forces, if a system has only what we call conservative forces, then the total energy is going to be conserved. And that word conservative forces, all that means is that that force is independent of the path that the object takes. Oops. Okay, so a conservative force, it's only going to depend on the position that the object has. So let's look at an example of this. One example would be gravity. Okay, gravity is a conservative force because it's independent of the path and only depends on the position of the object. So let's look at a couple examples of this and see what this looks like. Let's say we have a ramp that looks something like this. And then we have another ramp that's kind of curved like this. And at the top of each ramp, we have, let's say, a ball. And then in the third scenario, we're just holding this ball right here, and there's no ramp that it's going to roll on, and we're just going to drop it. So in all three of these situations, the initial position of the ball is the same, right? Because it has the same height. But there's going to be three different paths here. The first one is going to go down this inclined ramp. The next one has this curved ramp, and then in the third one, you're just dropping it. So regardless of these paths that it takes, the position change is going to be the same for in all three scenarios. Okay, so it's a conservative force. It's independent of the path because it has the same initial height. Now, an example of a non-conservative force would be something like friction. Okay, so friction does depend on the path. Okay, because if there's friction on these ramps, okay, then it's going to look a little different for the first two situations in comparison to the third one. Now, when there is a loss of mechanical energy in a system, it's usually goes in the form of thermal energy or heat. So, assuming there was friction on this ramp now, um, as the ball rolls down, then it's going to lose energy in the form of heat due to that friction. Now, in a system, if the energy is conserved, it can still transform from one type to the other. Okay, we've learned about three different forms of energy. We have gravitational potential, we have elastic potential of a spring, and we have kinetic. Okay, so I can transform from one type to the other. So in these three examples, you're starting with gravitational potential energy, and as it begins to move, it's going to transform or change to kinetic energy as it starts to speed up and the height starts to reduce. Now, a lot of times to kind of organize this and have a kind of representation of the energy within a system, we use what we call energy bar charts. And we started to see some of those bar charts in some of our practice problems. Okay, so they look something like this. And at the bottom, we have the different types of energy, kind of elastic potential, gravitational potential, kinetic. You can even have the total energy on your bar chart. And you just fill in the bar chart based on the different types of energy that you have at various locations within a system. So let's look at a couple examples of that and what those would look like. Let's say that we have a spring-loaded toy, and then it's launched, and let's say it's launched at an angle. So it does something like this. And we want to make some energy bar charts at some various positions um, before this is launched and even after. So before it's launched, if we assume this is a height of 0 and it's not moving yet, that would mean that we have no gravitational and we have no kinetic energy. But there is this spring here, so all the energy is just going to be elastic potential. So if I made a bar chart at that location before it's launched, and we'll go ahead and track the total energy here, then all the energy in the system is going to be this elastic potential. So these two would be the same, okay, because all the energy is this elastic potential. Let's say that it's launched, and let's look somewhere around here. And now the spring is no longer compressed, so you have no elastic potential. You do have a height, and it is moving, right? So you have a velocity. So the types of energy that we have at that location would be gravitational potential as well as kinetic energy. So if we made a bar chart there, we have no elastic potential. We do have gravitational, and it is moving, so we have some kinetic energy as well. Now the total energy, though, is going to stay the same as it was initially. So this bar would be the same as it was before. And in looking at your bar charts, this one and this one should equal this one. Okay, so 1 plus 2 should be the same as this third one here, because the total energy should be the same. Now let's look and say right here. So now you still have a height, but your height is smaller than it was here, so that means you're going to have less gravitational. Still no elastic potential, you have a velocity. So making a bar chart there, now your gravitational should be smaller than it was in the second situation or the second bar chart, meaning your kinetic should be larger. But again, the total energy should be the same as it was in the other two situations. So the energy bar charts are good at kind of describing the types of energy in various locations within a system. Let's do one more. Let's say we have an inclined ramp. And let's say at the bottom of the ramp, we have a wall, and on the wall, we have the spring. And at the top of the ramp, we have a cart, and let's say it's initially at rest. So we're holding it in place. And we want to look at the energy here before it's released, halfway when it's down the ramp, at the bottom of the ramp, and then after it comes to a stop and compresses this spring. So initially we do have a height. Velocity is 0, so no kinetic energy. And there's no elastic potential here. So your bar chart, before it's released, since its velocity is 0, no kinetic energy, no spring, that means all the energy of the system is gravitational. Now let's look halfway down. Halfway down, your height has gotten smaller. it's moving now, so you do have a velocity. Still no spring. So the two types of energy you have is gravitational potential and kinetic. And since it's halfway down the ramp, that means half of it is going to be gravitational, the other half is going to be your kinetic energy. So let's fill out our chart. Half of it is going to be gravitational, half of it is going to be kinetic. The total energy is going to stay the same. Now at the bottom of the ramp, now your height is 0, still no spring, so all of your energy is going to be kinetic. Again, total energy stays the same. And then lastly, once this cart comes and compresses the spring, comes to a stop, your height is 0, your velocity is 0, so all your energy is going to be elastic potential. So again, these charts are good to kind of show what types of energy you have in different locations. Now let's put this to a practice problem and kind of see how we could use this to solve a practice problem. And then we're going to solve this two different ways. I'm going to show you two different ways that you could do this. So we have a 4 kilogram object. It's at the top of a ramp. Height is 5 meters. It's moving, so it's initially moving 6 meters per second. And we want to know the velocity at the bottom of the ramp. So let's kind of draw our ramp here. Okay, so it is moving 6 meters per second. And it has a height, 5 meters. And we want to find how fast it's going right here at the bottom of the ramp. And we're going to use this conservation of energy to solve this problem. So at the top of the ramp, it is moving, so we have kinetic energy, has a height, so we have gravitational potential. So one way we can solve it is we can kind of break it down into before and after. So initially, you have gravitational potential and you have kinetic energy. So if we plug in our equations, we have mgh plus 1/2 mv squared. And we can plug in our numbers. So our mass is 4 kilograms. Height was 5 meters. All right, so our gravitational potential energy, we have 200 joules. In our kinetic energy, we have 72 joules. So the total energy at the top of the ramp is equal to 272 joules. Now, since energy is conserved, that means the energy before has to equal the energy after. So this is very similar to what we did in the momentum unit. We would find the total momentum before and set it equal to the total momentum after. We're doing the same thing, but now it's energy. So at the bottom of the ramp, we can assume it's so close to the bottom that it has a height of 0. So all your energy is going to be kinetic energy. So now we can say 272 joules is going to equal the kinetic energy at the bottom, so 1/2, the mass of the object, which was 4 kilograms, and then this final velocity squared. So now we're just solving for the final velocity. So your final velocity is going to equal 11.66 meters per second. Now, another way that we could approach a problem like this is making what we call a conservation equation. Okay, so before at the top we said we had gravitational and we had kinetic energy, and I'll put a T for the top. And we can set that equal to the kinetic energy at the bottom of the ramp. And if we plug in our equations, that would give me mgh plus 1/2 m, and I'm going to put initial velocity squared, equal to 1/2 m final velocity squared. And this is what we call a conservation equation. Now this comes in handy to do this because if you look at this, you should notice that every term has a common thing in there. It's the mass. So the mass actually just cancels out. And a lot of times in a problem, they won't give you this mass. And in order to solve it, you need to build your conservation equation, and then you can cancel out your mass. Okay, so if you're ever working a problem and you're kind of stuck and you're like, I don't have the mass, make yourself your conservation equation, and more than likely it's going to cancel out. So then from here, it would leave me gh plus 1/2 initial velocity squared equal to 1/2 final velocity squared. And now we just plug and chug. Okay, just plug in all your numbers and then solve. And you'll end up with the same answer, 11.66 meters per second.